This is the third lecture, and the title for this lecture is Elementary Signals in the Discrete Time Domain. Before we take up today's topic, I want to give you a couple of tidbits about last day's lecture, and one of them is to introduce you to two very outstanding scientists. One of them is Leonhard Euler. You remember we talked about Euler's relation e to the j theta equal to cosine theta plus j sine theta. If Euler was not there and he had not written this relationship, imagine what would have happened to science, technology and electrical engineering in general. Euler, a brief life history. He was born in Basel, Switzerland, the son of a clergyman. He graduated from the University of Basel in 1724 and joined the Russian Academy of Sciences in St. Petersburg, which was later changed to Leningrad. It has come back to the original name. In 1727, on the invitation of Catherine I, he served in a similar capacity at the German Academy of Sciences at the request of Frederick the Great in 1741. He was perhaps the most prolific mathematician of all times, even continuing to dictate books and papers after he became blind in 1766. He still found time for 13 children and 2 wives, the second of whom he took when he was 69 years old. Swiss mathematicians are still publishing his papers, and it is estimated that his works will eventually fill 60 to 80 large volumes. He was so prolific in his scientific contributions. The other name that we mentioned is that of Heinrich Hertz. The unit of frequency, cycles per second, as you know, has been renamed as Hertz, and this is Hertz. The brief biography of Hertz that I could get is that he died very young, only at the age of 37. He was born in Germany, in Hamburg, the oldest of 5 children in a prominent and prosperous family. After graduation from high school, he spent a year with an engineering firm in Frankfurt, a year of volunteer military service in Berlin, and then a year at the University of Munich. Finally, he entered the University of Berlin as a student of the great physicist Helmholtz. You heard about Helmholtz earlier? Okay. Hermann von Helmholtz. Later, Hertz received his doctorate and was a professor at Karlsruhe when he began his quest for electromagnetic waves. It was there that he met Elizabeth Doll, the daughter of one of his fellow professors, and after a 3-month courtship, they were married. Only a few years after his famous discovery, that is the radio waves, he first showed that radio waves as theorized by Maxwell did exist in practice. Hertz died on New Year's Day in 1894 of a bone malignancy at the young age of 37. His researches ushered in the modern communication age, and in his honor, the unit of frequency, that is cycles per second, was named the Hertz. This is about the two scientists. Then a couple of things couple of tricky things which we should have done in the second lecture, but we left out. One of them is, if x of t is an even function, what can you say about x of t minus 1? Is it also even? The answer is no. We'll find out. If you do not understand why, we'll find out later in the tutorial class. The other thing that I left out is the relationship between u of t and delta of t. since you know there is a formal difficulty in defining delta t is a unit impulse occurring at t equal to 0, the amplitude is infinitely large, but the area under the curve minus infinity to infinity delta tau d tau is equal to 1. The relationship between the two is that delta t is the differential coefficient of ut. There is a formal difficulty in doing this, and therefore it is better to look upon them as limiting functions. That is, what we do is, this is our ideal unit step. Now I consider a function like this, which goes to 1 at time delta, small delta, all right. Then its height, its slope is 1 by delta, because this is the time axis. The slope is 1 by delta. If we plot the slope versus time, if we plot the slope versus time t, then you see the slope is a constant of value 1 by delta, and this stays for time delta. It is 0 outside t greater than delta or t less than 0, and you see if you take this area is simply equal to 1, and you can easily see that u of t, if we call this function as u1 of t and this function as delta 1 of t, you can easily see that u of t is u1 of t under the limit that delta tends to 0. All right. Similarly, you see that delta t, the formal unit impulse function, is simply delta 1 of t under the limit capital delta tends to 0. These are two limiting definitions of the unit step and the unit impulse, and perhaps to an engineer these make much more sense, because in the laboratory you can neither generate a step nor an impulse. In the laboratory what you can generate is perhaps a steep rising waveform which approximates a unit step. In the laboratory what you can generate is a large pulse of short duration, and that is what perhaps approximates a unit impulse. There are a couple of properties of the impulse function which are of interest. For example, if I multiply x of t, an arbitrary function, by a unit impulse function, you see that because delta t exists only at t equal to 0, it doesn't exist anywhere outside t equal to 0, this should be the same as x of 0 multiplied by delta t, because the value of x that is meaningful is only at t equal to 0. This, in a more general form, suppose x of t is multiplied by delta t minus tau, where tau is a constant. Then you see this should be equal to the value of the left hand side exists only at t equal to tau. It doesn't exist anywhere else. So this is simply equal to x of tau delta of t minus tau. It is as if x of t is given over all possible values of time, and what we are doing is we are sifting out or sampling out one of its values at a specific instant of time. By multiplying delta t minus tau, we are multiplying by an impulse which occurs at t equal to tau, and it is as if we are sifting out or sampling out the value of x, the arbitrary function, at t equal to tau. More generally, if you integrate this from minus infinity to any value which is tau plus, that is a range in which the impulse function occurs, then this this also has to be integrated from minus infinity to tau plus. You multiply by dt, and since x of tau is a constant, it comes out, and the rest of the integral is unity. And therefore, by multiplying by a unit impulse, we are sampling out the value of an arbitrary function at the specific instant at which the impulse occurs. This is called the shifting, S-I-F-T-I-N-G, or sampling, S-A-M-P-L-I-N-G, sampling property of delta t, of the unit impulse function. And electrical engineers shall be greatly interested in this property, because this defines the rudiments of sampling, that is converting a continuous time signal into a discrete time signal. And it is actually done by approximations to impulse functions, but for simplicity we shall consider this sampling to be done by an impulse function. You shall see that analysis gets greatly simplified if we do consider sampling by an impulse function. Now we can consider the elementary signals in the discrete time domain, dt elementary signals. And in consonance with what we have talked about in continuous time signals, the two of the most important elementary discrete time signals are the unit step. Now it's no longer a function of small t is for continuous time function, it is of small n, where n is an integer, and u of n is defined like this. If this is your n axis and this is u of n, then u of n exists for all values of n greater than or equal to 0, and its value is equal to unity at all values of n, and therefore u of n is like this. And this continues ad infinitum. This is 0, 1, 2, 3, 4 and so on. U of n therefore is exactly like a unit step function in the continuous time domain. It is as if a sampled version of the unit step, sampled at equal intervals of time, and the time interval is discretized to integers. Actually, this interval shall be some value capital T, which you have normalized to 1. In the first lecture we had pointed that out. So this is u of n, and delta n on the other hand does not have this kind of an analogy. That is, delta n is not sampled version of delta t. That is the difference. Delta n is simply one single value, one single sample at n equal to 0, and the height or the value of the sample is equal to 1. So if we write analytically, u of n is equal to 1 for n greater than equal to 0, and it is 0 otherwise. On the other hand, delta n is equal to 1 only for n equal to 0, it is 0 otherwise. These are the two elementary signals, two of the most important elementary discrete time signals. You notice the difference. I repeat, u of n can be considered to be a sampled version of u of t. The height is 1 and it exists for all values of n greater than or equal to 0. On the other hand, delta n cannot be considered as the sampling of delta t, because the value of delta n is 1 only at a specific value of small n, namely n equal to 0. By the same token, if I say delta n minus half, can somebody tell me what this function will look like? Is it a shifted version?
Yes.
It is not, because the argument is not an integer. If it is a discrete time signal, it has to be, the argument has to be an integer. So delta n minus half does not exist. Poor function. On the other hand, if I take delta n minus n0, where n0 is an integer, that is the most important thing. n0 is an integer, then delta n minus n0 is a function which exists, which is equal to 1 at n equal to n0 and is 0 otherwise. So delta n minus n0, if n0 is an integer, is indeed a shifted version of delta n. The relationship, well, the other difference that I wanted to mention between delta t and delta n is that delta t, the amplitude is infinite. It's measured, it's defined in terms of its integral. On the other hand, in the discrete time domain, the amplitude is 1, and it does not have to be defined by an integration. An integration is impossible because it exists only at a specific value of n. Alright, what is the relationship between delta n and u of n? You can see that in u of n is 1 for all values of n greater than or equal to 0. If you retain only the n equal to 0 term and discard all others, that is, if you take u of n and subtract from it a shifted version of u of n, shifted by one sample, that is u of n minus 1, then precisely what you get is a delta n. Isn't that right? You retain only the n equal to 0 term, n equal to 1, 2, 3, etc. They get subtracted because of u of n minus 1 with a negative sign. Alright, so this is the relationship between delta n and u of n. And you notice that it is very similar to the differential coefficient in the continuous time domain. Here, it is not a differential coefficient, it is a difference. It is a difference. The difference of argument between the two is 1. So in a sense, it is an analog of the differential coefficient. The difference divided by the difference in the argument, which is unity, and therefore u of n minus u of n minus 1. On the other hand, if you take u of n and you take delta n minus, let's say, n0, alright, delta n minus n0 is a single pulse occurring at n equal to n0. Now if you superimpose such pulses at all values of n0 from 0 to infinity, that is, if you add such pulses, unit impulses in the discrete time domain from n0 equal to 0 to infinity, then obviously you get u of n. So u of n can be considered to be a superposition of an infinite number of unit impulse functions in the discrete time domain occurring at all values of the argument greater than or equal to 0. This relationship between u of n and delta n is extremely important, and almost all arbitrary functions can be expressed in terms of these two elementary functions, namely the unit step and unit impulse. Now, there are attempts to distinguish between these terms as far as continuous time domain and discrete time domains are concerned, but in the context of discussion it should be clear what we are talking about, and therefore we shall not enter into duplication of terms. We shall, if we say unit step, and if it is the continuous time domain that we are talking of, it is u of t. If it is discrete time, then u of n. It should be clear to you. So we shall keep the terminology the same. We next consider the third elementary signal, as we had done in the continuous time case, namely discrete time exponential. This is the third elementary signal of the discrete time domain. Now, discrete time exponential, exactly like the continuous time, we define as C, some arbitrary constant alpha to the power n. We have not brought the exponent or e, but you see, any arbitrary constant alpha can also be written in terms of e. If we put alpha equal to e to the power beta, then it is simply e to the beta n. That's how the exponential comes. So 2 to the power n, for example, is an exponential signal, because 2 can be expressed as e to the power beta. All right, any positive constant, positive or negative, it doesn't matter, to the power n is an exponential signal. We can consider, as in the CT case or continuous time case, we can consider the various possibilities for C and alpha. Suppose C and alpha are real, then the signal shall be real. All right. Well, since C is only a multiplying constant, that is, it determines the amplitude, let's normalize it to 1. All right. Let's normalize C to 1, and we consider various values of alpha. Suppose alpha is greater than 1, then naturally as n increases, the signal increases. In other words, if I plot C alpha to the n, what we will get is something like this. The amplitude of the signal shall increase exponentially. This envelope will be an exponentially rising envelope. On the other hand, if alpha is between 0 and 1, if alpha lies between 0 and 1, then the signal shall be an exponentially decaying one, because as n increases, alpha to the n, as n increases, 0.5 squared is 0.25. 0.5 cubed is 0.125, and so on. And therefore, as alpha increases, the signal decreases. The envelope, these are the individual signals, this is the envelope decreases exponentially. Now, let's see what happens if alpha lies between -1 and 0. If alpha lies between -1 and 0, negative value, then you see alternately they will become positive and negative, right? So what we will get is something like this. We will get exponentially decaying signal, but if this signal is positive, the next one shall be negative, because alpha is negative. The next one shall be positive, the next one shall be negative, and so on. Okay, this is the case -1 less than alpha less than 0. If alpha is less than -1, if alpha is less than -1, then you see alternately the signals will be positive and negative, but it shall increase exponentially. That is, it would be something like this. If alpha is less than -1, then if this signal is positive, the next one will be negative, and so on. It is an exponentially increasing signal. Now, these are as far as the real signals are concerned, C and alpha. Let's see, we'll have some fun if alpha is complex. Let's first consider the signal e to the power beta n, where beta is a purely imaginary quantity. Let's say beta is equal to j omega 0. Then the signal is e to the power j omega 0 n. And if you recall the corresponding continuous time signal e to the power j omega 0 t, you recall that this is always periodic. E to the j omega 0 t is always periodic. There always exists a capital T such that omega 0 times capital T is an integral multiple of 2 pi, always periodic. We shall see strangely that this is not always periodic. Before we see that, let's look at some of the finer aspects of this signal e to the j omega 0 n, capital omega. This is capital omega. You notice that e to the power j, if I increment omega 0 by 2 pi or any multiple of 2 pi, let's say k times 2 pi, n multiplied by n, what is the value? It is the same as e to the power j omega 0 n. This is because e to the j n k 2 pi is equal to unity. Alright. This is not true in the case of the continuous time signal. This is one big difference between a discrete time exponential signal, a complex discrete time exponential signal, and a complex continuous time exponential signal. If you increment small omega 0 by 2 pi or a multiple of 2 pi, the value does not become e to the j omega 0 t, whereas it does become here because small n is an integer. Now this brings out a very interesting fact which we shall utilize later, that is j omega 0 plus k 2 pi times n equal to e to the j n omega 0. This equation brings out a very interesting fact, namely that the possible values of omega 0 are only ranging from 0 to 2 pi. Isn't that right? If omega 0 is incremented by 2 pi, there is no change in the value of the signal. And therefore, if you are tempted to call omega 0 as the frequency, the discrete time frequency, then omega 0, the range of omega 0 is between 0 and 2 pi. If you don't like 0, if you want to make symmetrical abscissa, then you can take from minus pi to plus pi, because it does not matter whether you exceed this range by any amount that you like. You can always fold back or come back to the basic domain. The reflection of this in practice is that the angular frequency in discrete time case can have values only between 0 and 2 pi or minus pi to plus pi. That is, wherever you start, you stop after 2 pi, then that is the basic range. Capital omega 0 has a range only between 0 and 2 pi. Is that clear? When you study digital filters or digital signal processing, you will see that capital omega 0, which is the digital frequency, always is taken between 0 and 2 pi. Not just that, it is taken between 0 and pi. And the reason for that is the following. I want you to follow this carefully. Suppose we take a e to the j omega 0 n, and I have said that you have to consider only the range 0 to 2 pi, because outside this the complex exponential repeats its value. It is not against time. Time is characterized here by small n. We are considering variation of capital omega 0. We did not consider it in the case of a continuous time signal, because continuous time signals do not have this property. This property is peculiar to discrete time signals only. Now, naturally we go from 0 to pi and pi to 2 pi. And if we follow our common sense, then obviously as we go from 0 to 2 pi, the frequency is increasing. Alright? Peculiarly enough, what happens is, if we call frequency, what is frequency? Frequency is the rate of variation or rate of oscillation. Now surprisingly, the rate of oscillation, as you go from 0 to pi, if you plot the rate of oscillation, well, it increases, and then from pi to 2 pi it decreases. In fact, the frequency 2 pi is identical to the frequency 0. Capital omega 0 equal to 0, the value of the signal is 1. Capital omega 0 equal to 2 pi, the value of the signal is again 1, and therefore the frequency here and here are the same. So the frequency, this is quite contrary to what happens in the analog or continuous time signal, and therefore I am spending time on this to be able to impress upon you that it suffices in the discrete time domain to consider frequency from 0 to pi. All frequencies are here. So this is low frequency, this is high frequency, this region is high frequency, then again it becomes low frequency. Ultimately it goes down to 0. We started from 0. And therefore it suffices to consider from 0 to pi. Now why is this? I have not given any justification. Let's consider any frequency pi plus delta. Let's say this interval is delta. Then you see e to the power j pi plus delta is the same as e to the j pi multiplied by e to the j delta, which is equal to, what is e to the j pi? Minus 1. So minus e to the j delta. You see the frequency of oscillation, well, let's multiply by n now. We are generalizing now, all right. Pi plus delta multiplied by n. N is that time variable. J pi n, e to the j pi n can be plus 1 or minus 1, and therefore you should take it as plus minus. We are generalizing. Now you see that around pi, it does not matter which way we go, plus delta or minus delta, it is delta which is the angular frequency, because it is only the amplitude which is affected by pivoting at omega 0 equal to pi. And therefore in the angular frequency domain, as omega 0 goes from 0 to pi, the rate of oscillation increases, and as we go from pi to 2 pi, the rate of oscillation decreases. And this creates problems. It does sound very simple and logical and simplifying, because we don't have to consider infinite number of frequencies as in the continuous time domain. In the discrete time domain, it suffices to consider frequencies only from 0 to pi, because all frequencies are contained here. If you go beyond pi, then you shall simply, if you go equal distance on this side or this side, the frequency is the same, and therefore it suffices to consider this range, and this in communication parlance, as you shall learn later on, is called the base band. In digital communication, this is called base band. If you take the course on digital signal processing, also you shall come across this term, and signals shall be processed only in the baseband, because it does not make sense to continue processing, because you are simply repeating the frequency. If this point is clear, then you go to the question of periodicity of e to the j omega 0 n, the exponential signal. Well, since we are not sure whether this signal would be periodic or not, we say possible periodicity of e to the j omega 0 n. And if you recall the basic definition of periodicity, a discrete time signal x of n is periodic if and only if you can find a minimum number, capital N, such that x of n is equal to x of n plus capital N. If you can find a an integer capital N such that x of n becomes equal to x of n plus n, then yes, it is periodic. And the smallest value of n is known as the period of the discrete time signal. If we apply this criterion here, you see e to the j omega 0 n should be equal to e to the j omega 0 n plus n. Then you come up with this would be equal if and only if e to the j omega 0 capital N is equal to 1, which means that omega 0 times capital N should be equal to 2 pi or some integral multiple of 2 pi, m times 2 pi. Is that point clear? What we wanted is e to the j omega 0 capital N should be equal to 1. This leads to the equation that omega 0 capital N should be equal to either 2 pi or an integral multiple of 2 pi, which means that this quantity omega 0 should be equal to twice pi times a rational number small m by capital N. This is the condition for periodicity of the exponential signal e to the j omega 0 n in the discrete time domain. And you notice that this is indeed a very strict constraint. For example, a signal like let's take some examples. Cosine of n by 6, although it is a cosine function, it is not periodic. Why? Because omega 0 is equal to 1 by 6. It is not, it cannot be put in terms of 2 pi times a rational number. So this is not periodic, even though it is a cosine function. So cosine or sine or exponentiation in a discrete time case does not guarantee periodicity. For periodicity, this is the relation that has to be obeyed. That is, the coefficient of Jn must be 2 pi times a rational number. Let's take some more examples. Let's say cosine of 2 pi n divided by 12. Is this periodic? This gives omega 0 equal to 2 pi 1 by 12. And therefore indeed it is periodic with a period capital N equal to 12. Alright. On the other hand, if I take, let's say, cosine of, now be careful, 5 pi n divided by 12. Oh, let's make some more odd number. Okay, 31. Some number, 31. 5 is a prime number, 31 is a prime number. Now, can I write this? Can I conclude that it is periodic or non-periodic? The test is omega 0 is equal to 2 pi multiplied by omega 0 should be the coefficient of n. So I can write this as 2.5 divided by 31. Is that okay? Which I can write as 5 divided by 62, and therefore indeed this is periodic, because 5 by 62 is a rational number. But the period here, capital N, is 62, not 31. Is that clear? This is a big difference between continuous time signals and discrete time signals. Discrete time signals, although it's very tempting by looking at the signal to say that it is periodic, it may or may not be periodic. The essential condition is that omega 0, let me write down the essential condition. If your signal is e to the j n omega 0, it can be either in this form or in terms of cosine or sine. Alright. The coefficient of n, that is the discrete time integer variable, must be twice pi times some number small m divided by capital N. M by n must be a rational number. Alright. And therefore the period is equal to, if this is a rational number, period is n, which you can write as 2 pi m by omega 0. Is that correct? The period capital N must be 2 pi m by omega 0, and capital N, this is another test, capital N must be an integer, otherwise it is not a periodic function. Now, what is the fundamental frequency? You recall that in the continuous time case, the fundamental frequency is 2 pi by capital T, the fundamental angular frequency is 2 pi by capital T, and this is small omega 0, which we wrote as 2 pi times frequency in Hertz. Alright, here if I write frequency as 2 pi divided by n, then you notice that it is omega 0 divided by small m. In the continuous time case, it was simply small omega 0. In the discrete time case, it is capital omega 0 divided by m. I emphasize that you have to get to your heart the difference between periodic continuous time signals and periodic discrete time signals. We shall of course work out problems in the tutorial class about this elementary signals, the difference between continuous time and discrete time signals. After these three basic signals, that is u of n, delta n, and the exponential signal, that is c e to the power beta n. Let's see how these signals define a system. A system basically is defined by the type of signals that it handles. For example, if a system S takes in a continuous time signal x of t and produces at the output a continuous time signal y of t, then the signal S is known as a continuous time system. The system S is known as the continuous time, a continuous time system. It takes in an input, a continuous time signal, it gives out a continuous time signal, it is a continuous time system. On the other hand, if it takes in a discrete time signal x of n and produces a discrete time, another discrete time signal y of n, then the system is called a discrete time system. Now, one can ask, there are systems which take continuous time signals and outputs or produces a discrete time signal. And the most usual example of such a system is the A to D converter. A to D converter. It takes an analog signal and produces a digital signal. It takes a continuous time signal x of t, and maybe it produces a y of n. What would you call such a system? It's neither continuous time nor discrete time. So it's called a hybrid system. So a system can be continuous time, it can be discrete time, it can be hybrid. There is an inverse of this also, that is you take a discrete time signal and you produce a continuous time signal. This is also a hybrid system, and this system is D to A converter. Alright. A system, a big system, can almost always be decomposed into its subsystems, which means that you can take smaller systems and connect them meaningfully to make another system, to make a large system. And there are several types of interconnections that one is interested in. Suppose we have two systems like this, S1 and S2, such that the output of S1 is the input of the next stage of the next system, and the overall system produces an output here. To be more specific, let's consider a continuous time system, x of t. This produces y1 of t, and this output is y of t. Then y1 of t is an intermediate output or input. It is the output of S1 and the input of S2. The overall system, if we consider this connection as the overall system S, then obviously it is a connection between S1 and S2 such that the output of S1 acts as the input of S2. Such a system is known by the name cascade, C-A-S-C-A-D-E, cascade or series connected system, or there is still another name, tandem connection, tandem, T-A-N-D-E-M. Such a connection is extremely useful in practical engineering. For example, if you want an amplifier with a gain of, let's say, 1000, then it may not be possible to get it with a single amplifying stage. You may have to use more than one stages. Then what you do is connect two or more amplifiers in cascade or in series or in tandem. In a similar manner, because I use the term series, there exists parallel connection of systems. If we have two systems, S1 and S2, which receive the same input, that is, to be specific, let's say it's a discrete time system, same input x of n goes to both the two systems, and the outputs of S1 and S2 are added together. Outputs of S1 and S2 are added together, and this is the overall output y of n. This is y1 and this is y2. Then such a system is known as a parallel connection of systems. A parallel connection, for example, is used in alternators, when you require more power, more energy than a single generator can supply. What you do is you parallel two generators, parallel connection of generators. Or in the case of a stereo amplifier, the final stage, the power amplifier stage, you want to produce a 20-watt music, and you have two amplifiers, each can give you only 10 watts. Then you connect them in parallel. That is the same signal you apply to both, and then you mix the two outputs. Mix. Here I have shown simple addition. You might mix in such a manner that one of the channels amplifies the bass, the other channel amplifies the treble, and you might mix them in a certain proportion which is more pleasing to your ears, and then whatever be the proportion, the connection is a parallel connection. There can also be combinations of series and parallel connections. For example, you can have a system S1 in series or in cascade with S2, and you can have a system S3, and they can run in parallel. This is the overall output. You can have another system here, let's say S0, and this can be your basic input. All right? You can have such connections, series and parallel combinations of them. The third important connection of systems in practice is the so-called feedback connection. And you have already studied feedback amplifiers, and you know that in a feedback connection there are two systems S1 and S2 such that from the output of S1 the output of S1 is fed to another system S2, which feeds back to the input of S1, that is, there shall be a mixer like this, and then the output of S2 is mixed with the input to make a modified input to S1. This is the feedback connection, and the usual feedback that is used in practice in engineering is negative feedback. In other words, the signals usually subtract from each other. Negative feedback. But feedback is also a basic connection for engineering systems. We shall conclude this lecture by introducing to you a particular kind of systems, that is systems with memory, systems which can remember. Take a capacitor which is initially charged to a certain potential, let's say V0. A capacitor C which is charged to a certain potential V0, and then at time t equal to 0 you introduce a current I of t. You connect a current generator across this at t equal to 0. Let's say we have a switch which normally remains closed, it's opened at t equal to 0. Then this current generator shall charge this capacitor, and the voltage Vt at any instant of time shall be 0 to t I of tau d tau plus the initial voltage V0, where I have made a mistake. Can you see what the mistake is? This is the charge, so it must be divided by capacitance to get the voltage. Now you see this capacitance, even though excited with a source I of t from t equal to 0, it does not forget what it had at negative t, at t less than 0. It memorizes, it keeps in its memory the voltage V0. So a capacitor is a system, a single capacitor is a system with memory. A system which has no memory is known as a memory-less system. Another name for this is the instantaneous system. If you have understood the general concept of memory, then it is not difficult now for me to formally define what is a memory-less system and what is a memory system. A memory-less system or an instantaneous system is one in which the output at any instant of time, I could define in terms of continuous or discrete time, it doesn't matter, at any instant of time depends only on the present input. If it does, then it is a memory-less system. It does not remember what the input was an instant ago. For example, a resistor. You know the current is the voltage divided by the resistance, and the current changes instantaneously as the voltage changes. The present instant current is determined by the present instant voltage only and nothing else. On the other hand, if there is a system which gives an output depending on what the present input is and also the past inputs, then it is a system with memory. For example, y of n, let's consider a discrete time system in which y of n is equal to x of n plus x of n minus 1, then it is a system with memory. Suppose there is a system y of n which is summation, let's say k equal to 1 to let's say n, x of k. Is this a system with memory? Yes, it depends on x of n and also x of n minus 1, x of n minus 2 and so on. On the other hand, let's say we have a system with x of n minus x squared of n whole to the power half. Is this a system with memory? No. This is a memoryless system or an instantaneous system. The final word that I want to say is that a system with memory is also popularly known as a dynamic system. Resistor is a static component. It does not have memory. A capacitance and an inductor, they are systems with memory because they are dynamic elements. We shall consider more about the classification of systems and various kinds of systems in the next lecture. Thank you.